Thank you for introduction. It's an honor to be here, and I could arrived here. So, let me introduce quantum computing. So slightly away from the main topic of this workshop, but I think it would be interesting for you, all of you. Yeah. So let me introduce quantum annealing. After that, let us consider the application of the machine learning, application of quantum annealing to machine learning. So I'm Masayuki Ohzeki from Tohoku University, but I have some cross appointment with Tokyo Tech. So, and I have established some startups in Japan, Sigma I. So in Japan, we have a slightly fever of quantum computing. So, and many of the startups was established. So, and as a researcher, we ourselves establish two academic and two business, and so by use of our research power. So this is a Sigma I. So for example, maybe you know that here is Tomoyuki Obuchi of Tokyo Tech, and here is Shu-In Kyo-san, and some of the members belonging to some community of the statistical mechanics or data science or machine learning. So anyway, so let me start my talk by introducing the quantum annealing. Maybe you know, all of you know some concept of the quantum annealing to manipulate or control the strength of the quantum fluctuation to solve the optimization problem. So the quantum annealing is to solve the combinatorial optimization problem. So you know the combinatorial optimization problem includes discrete variables. So and we consider some cost function to be minimized or maximized, and with some constraints. So and you know the many applications exist in industry, in sense of the benefit, in sense of the business side. So, however, it often takes a long time, exponentially long time to solve them. So, according to the increase of the number of the variables, so you know that this kind of the problems is belonging to the NP-hard hierarchy. So, the quantum annealing is a method to solve combinatorial optimization problem. So then we consider rewrite the cost function in terms of the Ising model. So here is a Hamiltonian or energy function or cost function of the optimization problem. So x denotes the binary variables. In this case, x denotes a 0 or 1 binary variables, but you can read this cost function is Ising spin glass problems. So then the xi and xj denotes the spin variables, up direction and down directions. So you see this problem is Ising spin glass problems. So and the quantum annealing is now implemented by hardware, real hardware. So then the problem is restricted to the be written by the quadratic unconstrained binary optimization problem. So you use now digital computer. So digital computer is in some sense a wide capacity. So we can write a program. So anything cost functions, any types of the cost function, and any types of the constraints. And we can encode some algorithm to the digital computer. But in the sense of the quantum computer, this is not developed and established, so therefore there are some restrictions. So we can have to write down the real application in terms of the cost function is written by the quadratic unconstrained binary optimization problem. This is one of the bottlenecks of current situation of the quantum annealing. So anyways, the quantum annealing uses quantum superposition for searching the ground state or lower energy state from all the combinations of the spin configurations or binary variables. So here is a picture of the hardware of the quantum annealing. So you know this is the current version of the quantum annealer. So D-Wave 2000Q. So D-Wave 2000Q implements a 2048 qubit. So D-Wave systems, Canadian startups established implement the quantum annealing in their superconducting device. So on superconducting qubit and with 2048 qubits. So but as stated before, however, on the current version of the D-Wave 2000Q, we have some restriction. So we have to write down the cost function in terms of the quadratic function, so Ising-Spin-Glass Hamiltonian, and some restriction of the connectivity between the qubits or some circuits. So then the interaction is restricted on the sparse graph. So in particular, the chimera graph we called. So therefore, if we have some cost function, but we consider to embed the original program into the sparse chimera graph. So therefore, we have to consider some optimization program to embed the original program into the quantum hardware. So then the worst case, only 64 variables can be dealt with by this machine, this device, even with 2048 qubits. So this is due to the limitation of the circuits. So and only quadratic function can be implemented. So therefore, if you consider, so yes, the quantum computing application to the machine learning. So the quantum annealer D-Wave 2000Q is a current version of the, in some sense, quantum computers by use of the quantum superposition. So without any programming in terms of the quantum computing, but you can solve the optimization problem by use of the quantum nature, by use this machine. But in machine learning, we often consider optimization. For example, weight of a neural network. Of course, the original program of the machine learning is not a combinatorial optimization problem, but we want to extract some feature of the quantum mechanics to apply to the machine learning. So then this machine cannot implement non-linear functions, non-linear transformation. So in neural networks, we often use non-linear transformation and the transformation combination of the transformations. So then, but this machine cannot implement a non-trivial non-linear transformation. That's a bottleneck. So better, please take this home message. So the quantum annealing originally a method to solve combinatorial optimization problem, and the cost function should be written by quadratic unconstrained binary optimization problem. So but after my talk, not only the quadratic function can be implemented, so you can implement non-linear transformation into this machine by use of the statistical mechanics. And then we apply our method to the optimization of deep neural networks. So let me introduce outline of the quantum annealing, or let me review the outline of the quantum annealing. So the first, the formulation optimization program in terms of the quadratic function into the H0. So H0 is a spin-glass Hamiltonian, is Ising-Spin-Glass Hamiltonian. Sigma denotes the binary spin variables. So the hat denotes the operator in the quantum mechanics. So then introduce a quantum fluctuation, creating a superposition of the spin variables. Typically, we use a transverse field. So this is a transverse field Ising model you may consider. This, at first, we consider the strong transverse field. For example, this is a coefficient for the strength of the transverse field. So f of t is some schedule for the quantum annealing. As first, ft is 0, set to be 0. So then the system is only with the transverse field. So therefore, the system is in the superposition of the spin variables. This is the ground state of the system. So starting from the ground state, trivial ground state, and slightly, so we are decreasing the strength of the transverse field, so increasing the strength of the target Hamiltonian, problem Hamiltonian. So then following the adiabatic quantum evolution, so you can find the non-trivial ground state of the Ising spin variables, Ising spin graph problems. So this is a quantum annealing or quantum adiabatic computation. So this is, we have some theoretical assurance for the quantum annealing. So according to the quantum adiabatic condition, so then we can have a non-trivial ground state after the quantum annealing process. So bad news, the p-hardness of the problems remains, even by use of the quantum mechanism of the quantum fluctuation, even by use of the quantum annealing. So in that sense, quantum annealing is not some solution for the solving the difficult optimization problem, but the good news is quantum annealing is a generic solvers. So it can accept any types of the Ising spin glass problem. So most of the combinatorial optimization problem can be written by the Ising spin glass problems. So therefore, quantum annealing attacks deal with most of the combinatorial optimization problem without any consideration further. So and if we implement further complicated interactions in the quantum system. So for example, the transverse field is only the single body terms of the X power X matrix. So then, but if we implement X interactions terms, for example, antiferromagnetic XX interactions, so there, in that case, we cannot perform the simulation in the digital computer efficiently. So because if you use the quantum Monte Carlo simulation for implementing these quantum systems, so then we consider some path integral formulation. So then you encounter some negative sign problem. So therefore, you can't simulate these XX antiferromagnetic XX interactions efficiently. So but on the quantum hardware device, we can implement, if we can implement XX terms, we can simulate efficiently the quantum non-trivial nature. So then, if we implement XX interactions, that would be a QMA complete. So this is a kind of sum of the wide class of the computations. So this is the direction of the updating the quantum annealing. So anyway, so since the proposal of the quantum annealing, so the 1998, done by the Tadashi Kadoaki and Professor Hidetoshi Nishimura, as a pure science, so they proposed the quantum annealing concept of the quantum annealing, but now implemented by the Canadian startup D-Wave Systems and commercialized. So D-Wave systems or D-Wave machines is the first commercial quantum computer, in some sense quantum computer. So and many institutes and in North America and companies implement. The first customer was Lockheed Martin. The second customer and NASA and Google collaborations and Los Alamos National Laboratories and Oak Ridge National Laboratories. And recently, we have some startup of quantum computing in Japan. So in Japan, our startups makes a largest ever quantum cloud access contract with the web systems. So now in Japan, we can use the web machine without any fighting. So you can use the web quantum annealer like that. So let me demonstrate the quantum annealing. So this is some login this window of the D-Web 2000 D-Web machine. So if you have some account of the D-Web machine, you can log in. So and we can encode some programs with quantum annealing. So by the MATLAB or Python, so measure coding program, and C++, like that. So very easy to use. So now on the browser, I demonstrate how to use quantum annealing. So now access by some wireless RAM. So don't memorize this API tokens. So anyway, you can set some parameters for the performing the quantum annealing. So for example, the answer mode and the number of the leads. So number of the leads means iteration of the quantum annealing. So default number was 10, but you can change the number of the leads. And so maybe yes, here is maybe interesting. So post-processing mode. So default is some low data from the D-Web 2000Q, and sampling mode you can choose. So sampling mode is this device, D-Web 2000Q, generates some sampling sequence of spin variables following the Gibbs-Boltzmann distributions. So therefore, very quick samplers we can use. And here is the optimization mode. So here is the chip of the quantum annealer. So you count the number of the qubits, 2,000 about 48. So this rectangular denotes a unit like this. So the vertical and the horizontal 4 by 4 qubits. So 8 qubits is a 1 unit. So and you can access directly on this qubit. Yes. So then you see some connection between different qubits. So then you can change the strengths of the interactions between the spin variables. The +1 denotes antiferromagnetic interactions, and -1 is denotes ferromagnetic interactions. And you can set some bias, local magnetic field like this. So we have some random spin glass problems like that. So with the 2048 qubits. So then you solve this problem 1,000 times. So by saying yes, now we solved. So 2048 spin glass problems we send. So then we have thousands entries of the solutions. So you see the lowest energy candidate like this. So you see the +1, -1, -1. So the solution done by with spin variables. So there is some histogram or profile of the solutions. So you see some different solutions. So the default time for solving the optimization problem or Ising spin glass problems on the D-Web 2000Q is like that, 20 microseconds, very quick. 20 microseconds per samples. So you set a number of the leads thousands, so then the 20 milliseconds. You can have a sampling sequence of Ising spin glass problems of the 2048 variables. Yes?
What would the comparable classical time?
Please try it. But very quick, because you need some relaxation time for generating the sampling sequence of the spin glass problems. So, for example, the sampling the thousands candidates, if you have some distribution function on the digital computer, is very comparative. But we have to prepare distribution functions just before the sampling. So the relaxation time is very long in general. So typically, this is a spin glass problem on the shoot two-dimensional lattices. So therefore, minutes we need to generate distribution functions, typically. Yes, turning on the next slide. Yes. So this is a picture of the hardware device. In this black box, you see some dilution refrigerator. So from top to the bottom, the refrigerator cool down to the absolutely 0 kelvins, 40 millikelvins on the processor chips. So on the processor chip, we have a superconducting qubits. So this is some schematic picture of the 1 qubit. So the direction of the current denotes spin variables. So for example, right direction is up, the left direction is down, for example. So this is the actual shape of the circuit. The rectangular circuit denotes the superconducting qubits, and we assemble superconducting qubits like this. So the cross section here is an interaction between the superconducting qubits. So you can tune the strength of the interactions and the local magnetic field for each superconducting qubits and for each pair of the superconducting qubits. But the limitation of the design of the hardware or circuit, so the limitation, some connectivity of the problems. So therefore, we have to embed original problem into this sparse particular graphs. So that is a bottleneck. Anyway, so since the proposal of the quantum annealing, so after proposal, we take the 20 years. The first commercial D-Wave machine was 2011, and after appearance of the commercial machine of the D-Wave machine is every 2 years. So they update the hardware. The current version is 2048 qubits. The next version will be implemented with 5,000 qubits. The name will be the D-Wave advantage, and with some more dense graph on the chips with some improvements. So So this machine is extremely low power consumption for computation. Of course, for the dilution refrigerator, they use 20 kilowatt for refrigeration. But for computation, 20 femtowatt. Because we use quantum superconducting qubits, so therefore you can use some eternal current on the superconducting qubits and without loss of the electric power. So this is one example for the benchmark. That was 2016, and then collaboration was done by the NASA and Google's for solving some optimization problem. So the vertical axis denotes the time for finding the ground state, and the horizontal axis denotes the size of the problems and the number of the spin variables. So therefore, increasing the number of the spin variables, so then it will take a longer time for solving the optimization problem. The red curve denotes done by the simulated annealing for solving the optimization problem. So the green curve denotes the quantum Monte Carlo simulation. So quantum Monte Carlo simulation imitates the behavior of the quantum annealing machine. So by introducing the quantum fluctuation and by considering some path integral representations, so then solve the optimization problems. So but on the D-Wave machine, without any representation by use of the path integral because the wave machine naturally evolves Schrödinger dynamics and naturally implements the quantum many-body systems. So therefore, extremely down to the time for solving the optimization problems. So 100 million times faster they reported. So but this is one of the benchmarks. So the NASA and Google chose some good problem for the quantum annealing. So therefore some findings beating the digital computers by the quantum annealer. But typically, if you generate random spin glass, Ising spin glass problems, and you compare the time for solutions, so then the quantum Monte Carlo simulation, the D-Wave 2000Q is around 10 or 100 times faster D-Wave. Yes. So in that sense, the quantum annealing is some variable and interesting for solving, for attacking the many-body problems.
Excuse me?
Yeah.
On this graph, there's quite a lot of spread for the D-wave curve. Where does that come from?
Due to the environmental noise. Because yes, because that is a good question. Because we have solutions from the D-Wave 2000Q now. Yes, again, yes, and then you see the solution data, so list of the data. So then the fluctuation among these samples. So this is due to the environmental effect, in some sense a thermal effect. So then the D-Wave 2000Q implements a quantum fluctuation and naturally attacked by the thermal fluctuation. So in that sense, quantum many-body systems in finite temperatures. So then yeah.
How different are these? Because I mean the first two seem the same so far.
Sequence.
Of course, there is something more, but can you also see the overlap or?
Of course,
and,
you.
Like evaluate how many, how far are these ground states? Sampling?
Of course, depending on the problems, but you can observe the distance between the, in some sense, Hamming distance and the distance from the ground state and the energy gaps, or yes, something like that. You can observe, yes. For example, in this case, energy is very close. Yeah. Yes, anyway. Yes. So now, and yes, we show some applications list. So because in Tohoku University, we have some groups for using the D-Wave 2000Q and the Tohoku University Quantum Annealing Research and Development since October 2017. And we perform advanced research with quantum annealer. So, and some creating the consortium among the companies in Japan for quantum annealings. So, and we have established two of the startups. The first one is JIJ Inc. So, creating some software for using the D-Wave 2000Q or some using models, using some hardwares. So, and the second was Sigma I. So, implements the D-Wave 2000Q and provide the machine time and with some benefit research engagement. So the collaboration between the Tohoku University and some companies in Japan. The first one is Denso and Kyocera, KCCS and NOMA and ICNW, and more secrets we cannot say anything. But anyway, so we perform many collaborations between the university and the companies. The first is normal asset management by predicting the stock attractiveness by use of the Boltzmann machine learning. So they have many of data of stock. So then the learns from the data by use of the Boltzmann machine learning. So because DWeb 2000Q generates the samplings of spin variables quickly, so therefore this is some acceleration, some accelerator of the machine learning, Boltzmann machine learning. So then they perform the learning, the stock attractiveness, and they compare some result of prediction and with real data. So then some uplift, actually uplift they observed. And with Cursor, they perform the quantum annealing on the problems of the quantum chemistry. So in the quantum chemistry, they want to minimize the energies of the quantum many-body systems. So then, we have to use many of the pre-processing and post-processing and solving the oscillating equations. So in the pre-processing, we have to consider the graph partition problems on the quantum many-body systems. So then the previous standard methods is failed to find some clustering of some molecules, some nasty structures found, but by use of the quantum annealing, they find some natural clusterings of the quantum molecules. And this is done by the high school students. Hachinohe High School students, they consider the optimization of the bus scheduling between the Hachinohe Station and the Hachinohe High School. So, and they considering the keeping the congestion, while reducing the number of the bus, but they keeping some performance of the bus commutation. So, and I think the AW, they consider some acceleration of the learnings. They consider the boostings. So boosting is considering the combination of the learners classifiers. So then they prepare some weak learner, weak classifier for some programs. So they consider the quantum annealing for selecting the good weak learners. So for increasing the generalization performance. So then they attain the speed ups of the learnings. And with denser corporations, this is optimization program. So in the plant, real plant. So the green dots denotes the movement of the automated guided vehicles. So the blue circle denotes increase the number of the times, congestions. So this denotes waiting times of the automated guided vehicles. So this is a current situation in real plant. But if we consider optimization problem, and by solving the quantum annealing, so then yes, they observe the smooth movement of the automated guided vehicles like that. So, and reduction of the size and the numbers of the blue circles. That means reduce congestions. So, and this is done by the Tohoku University. So, and we consider some good systems for evacuation from disasters. Yes, and this is a movie created by myself. Sorry, it's Japanese, but we use DWeb 2000Q for solving some optimization problem for tsunami evacuations. So we, Tohoku University, have encounters of the big earthquake 2011. So after that, we have some attacks from the tsunami, big tsunami, tidal waves. So then we consider we have some inspiration of the applications of quantum computing. So we have some simulation data of the tsunami. So then after that, we reflecting the result of the simulation of the tsunami. So then we consider the optimization problem, route directions, route guidance for evacuation from the big disasters. So this is a demonstration movie. So this is, for example, many of the users uses some smartphone map applications, and by considering their own shortest path. So then you observe some congestion on this bridge. Yes, here is the rivers, and we have some of the bridges. So then many of the users, so 100 users are suffering from the congestions for evacuation in tsunami. So, but if we consider some optimization problem, here is the energy function. So then we perform the optimization. So then some scattering of the cars and the reduction of the congestion for each bridges, so efficiently escaping from the congestion and from dangerous spots. So this is some applications, demonstrations of quantum annealings. So, but yes, you want to know the is it capable to apply quantum annealing to the machine learning? So this is some schematic picture on the quantum annealing. So the first quantum annealing is a method to solve the combinatorial optimization problem. And the cost function is only written with a quadratic unconstrained binary optimization problem, so Ising-Spin-Glass problems. And the quantum annealer makes a sequence of binary strings. So quickly, we can have a sampling of the binary variables, spin variables, quickly, 20 microseconds, one shot. So, and the ensemble is the ensemble is considered to be the following the Boltzmann distributions. Yes, gives Boltzmann distributions. Therefore, this quantum annealer is some accelerator of the Boltzmann machine learning. Yes. So, and the original motivation of the quantum annealing is for solving the optimization problem. So, in the case of the machine learning, so you usually often consider the optimization weight of the neural networks. But neural networks, weight of the neural networks originally consisting of the real valued weight. Yes. So, and the other machine learning technique is Boltzmann machine learning. So then needs Boltzmann distribution. So in that case, very good test bed for applications of quantum annealing to the machine learning. Yes. And the third one is boosting. The boosting is considering the combination of the weak learners. So in that sense, we consider some combinatorial optimization problem in this problem. Yes. The remaining problem is here. The two of the applications of the some Ising variable or quantum annealing to the machine learning is the best good choices, but typical or most of the users of the machine learning are interested in the neural networks, but the neural networks, weight of the neural networks consisting of the real valued weight, not discrete variable. Okay. But let me consider application of the quantum mechanics to the neural networks. So this is done by the 2018 by Mao group. So we propose some quantum atom. So atom is some standard tools for optimizing the neural networks. So and we consider some quantum version of the atom. So then very easy. introduce non-commutable operators in deep neural networks. So for example, so A denotes weights of the neural networks. So then we consider the non-commutable operators something like momentum, like that. So then we introduce kinetic energy like this. So then we consider the density operator like this. So the L denotes the loss functions of the neural networks. Yeah.
What is G?
I forgot. Sorry. Maybe the G is originally yes, weight of the neural networks. Sorry. So you consider the optimization programs of the weight of the neural networks with loss of the loss functions. So then we introduce quantum fluctuation. Yes, that is the problem settings. So then we consider virtual quantum system by considering the path integral representation like this. So then we banish, we can remove the operators. Instead of the quantum operators, we use a classical scalar variables like this. So then we have to introduce some imaginary time degrees of freedom. So then we consider some composite distribution functions for the systems. So then you see from the non-commutable operators, we find some attractive force between the parallel neural networks. So interacting is between the parallel neural networks. So then we have parallel computing for realizing the virtual quantum systems by considering the optimize these quantities. So then you see some gradient method. So M denotes the gradient of the loss of the functions. So and AT is the weight of the neural networks for each layers. So we consider here is the original some gradient descent. So and the width here from here with some attractive force between the different layers. Sorry.
What is quantum in the last equation?
Quantum.
What is quantum?
Correct? Here.
No, but A.
Here?
This update rule. No, the last equation.
Here.
A is the weights.
Yes.
Are they quantum?
Yes. The quantum operator is originally the yes.
The last equation.
Yes, the equation.
This is the update rule, right?
Update rule, yes.
In the last equation, A are still quantum variables?
No. This is a classical variables. But originally the quantum systems, so then we consider the path integral representation. So they introduce imaginary times, in some sense, a replica of copies of the neural networks, so denoted by the T's.
Okay.
So then
What is M?
M is the gradient of the loss functions. Yes. So here is a standard gradient descent and some with a non-trivial effect from the quantum fluctuations. So then you perform the parallel computing according to the imaginary times. So then you see some uplift of the test accuracy. So this is we consider some classification problems for the MNIST dataset and the Rivetti face recognition dataset. The horizontal axis denotes the number of the iteration epochs in the running. So the vertical axis denotes the test accuracy, and we overlapping plot for each rounds. So this is done by the classical Adam. So classical means without any further any quantum effect. So and with the quantum effect, with observed uplift of the generalization performance. Yes. So the bold curves denote the average performance, and the thin curves is the maximum performance. Yes, like this. So the right panel, on the right panel is performance for the face recognition Olivetti. Three layers. Yes, fully connected. Very simple construction of the deep neural networks. Not so deep. Because we have to consider the parallel computing, yes, very harmful computations. Yes, it is unsuccessful, but computational cost is very harmful. So therefore, this is not realistic. So, but anyway, so this problem, we focus on the understanding of the performance. So then the attractive force coming from the quantum tunneling. So here, non-commutable operators. So then we consider some approximations. So assuming the large coefficient of the lambda, so lambda denotes the strength of the quantum fluctuation. So then we consider some, so the weight of the neural networks is fluctuating around the mean of the neural networks over the imaginary times. And some computations by the use of the Fourier transformation, we have some quadratic form of like this. So that means fluctuation around mean neural networks. Mean neural networks is. And BT is a fluctuation around mean neural networks. Yes. So the VTT denotes the correlation between different samples on the different imaginary times. Now we consider some path integral representation of the systems. So and yes, we take the bold approximation around the classical path. Classical path means mean neural networks A. Yes, like this. So then, yes. We can reproduce entropy stochastic gradient. So Bardashian and Ricard Zekin was done on this machine learning papers. So entropy stochastic gradient is reproduced by the considering some approximation of the quantum stochastic gradient or quantum effect. So then the update rule is like this. So then here is the computational cost is extremely reduced. And we can some entropic effect, so effect from the fluctuation. So then as they reported, we can obtain some local wide minima, local wide flat minima solutions from this method. So in the quantum atom or quantum stochastic gradient descent includes this effect and non-trivial effect beyond entropy stochastic gradient descent, because quantum stochastic gradient descent without any approximations, of course the computational cost is very harmful, but yes, includes non-trivial effects. But if we want to use some properties or some uplift of the quantum mechanics, we have to implement some optimization program on the quantum many body systems without any approximations. So on the digital computer, we have to make some approximations to implement the quantum mechanics to the digital computers. For example, path integral representation. After that, for reducing the computational cost, we have to consider some approximations. So then the resulting is like this. But our hope, our main purpose, aim is to elucidate and to get some feature of the quantum mechanics. So then, by the way, so real quantum annealer, how behave? So this is a very simple optimization problem. So this line denotes the ferromagnetic interactions between the different spins. So then we apply the magnetic field up direction and down direction. So then the problem has many degeneracy in the ground state. So the ground state is 17 we have. So then the structure of the energy function is like that. This is the isolated ground state here, and most of the ground state is here, like this. So then, yes, let us perform the quantum annealing on the hardware. So the solution is located here. So, like local sharp minima does not exist from the output quantum annealer. That means quantum annealing actually affected by the thermal effect, but mainly affected by the quantum fluctuation. So the machine keeps a finite strength of the quantum fluctuation even at the last of the quantum annealing. So then the solution is takes wide flat local minimas caught in the wide local flat minimum. So therefore, if we use the quantum annealer to optimize neural networks, so then you can have a generalization performance by use of the quantum fluctuations. Yes, so then let us reconsider the optimization problem of neural networks in terms of the statistical mechanics. So we consider the partition function like this. So this is a cost loss function of the neural networks. So and we apply the constraints. Non-linear transformation. So phi denotes a non-linear transformation, and here is a linear transformation. So L denotes the number of the layers, and D denotes the number of the details. Yes, if we consider some system or many body system like this, so then the W denotes the weight of the neural networks. So then W is typically the same behavior of the neural networks or optimization problem of the neural networks like this. So then use Fourier integral representation of the delta functions with auxiliary variables. So then considering the zero temperature limit, in-row temperature limit, so yielding the post-optimal solutions. So then we perform the saddle point method. So then you have two of the sets of the equations. The one is a forward process, and the other one is a backward process. So this is a generalization of the backpropagation method in optimization of neural networks. So then, the system has some distribution function of the weight W. So then, the distribution function can be written by the local field for the W's with some coefficients determined by the data and determined by some result of the layers. So anyways, W is now is interpreted by the programs of with the local magnetic field. So therefore, this can be implemented in the quantum annealer because this form is yes, single body interactions, no quadratic, no even no the quadratic optimization problem.
Not binary.
Yeah, binary. Yes. Very simple binary problems. Yes.
But Y and Z are binary?
Sorry? W.
Y and Z.
Y and Z is not binary because we consider some non-linear transformations and combinatorial some combination, linear combination of the binary variables like this. Yes.
So how do you implement something that needs binary variable?
Sorry.
You're lost here. You say this is implemented with quantum annealer where you
Yes.
use binary variable?
Yes, W is binaries.
W is like
Binaries. And Y and Z is a real varied.
So it's
Yes.
a linear cost function. So it's a linear cost function.
Linear cost. No.
It's linear.
Because including the Y and Z and non-linear transformations. Yes, affected by the nonlinear transformations, the y and z is tuning by the nonlinear transformation, so including the non-trivial effect of the nonlinear transformation. But on the w, this form is very simple. Yes.
So you use here the dependence of y and z on w?
Yeah. By solving this forward process, yes.
Then it's not quadratic, it sounds.
Yes, whole the system is non-trivial, yes. So, but only on the weight is very simple. So some reformulation of the problems of the optimization problem in neural networks. Because if we have this form, we can implement this problem into the quantum annealers. So then we can perform optimization problem by use of the quantum annealer, and even by use of some regularization for the weight in some quadratic forms. So actually, we test by use of this strategy for optimization of the neural networks. So this is a very simple binary classification problems, and but with nonlinear transformation. So then you see there's some gradually increasing the performance of the networks in the D-wave quantum annealers. So actually, we implement 3 layers neural networks for the classifications of the binary problems, binary classification problems. So yes, you see the binary classification is successful by using the D-wave quantum annealers. So now we use, of course, we can use expectation value of the W's. So W is binary variables, but if you use expectation value of the W's, so then the W can imitate the real values. But if you only focus on the binary representation of the neural networks, so these researchers proposed binary connect. So binary connect is weights of the neural networks is binary variables. So then they consider perform the optimization neural networks with real valued networks at first. After that, they take the binarization of the result. But if we implement this strategy, directly optimize the binary connection, binary neural networks. So binary neural networks itself is a combinatorial optimization problem and very hard to solve directly. But if you use the wave quantum annealing and by use of this strategy, and you can directly optimize binary weight of the neural networks. Yes, this is a summary, and we have reviewed the quantum annealing and introduced some techniques by use of the statistical mechanics. So the result, not only the quadratic function can be implemented, and we apply our method to optimize the neural networks of binary weights. So, but this is just a starting point of application of quantum annealer to DNA, deep neural networks. Yes, that's all. Thank you.